Hi there. This video is for section 7.3, and I'm going to try to show you how to find integrals using the method of trigonometric substitution. And this is a technique that we do without using technology. And the book calls this integration by trigonometric substitution. I think it's a little bit misleading because we're not really integrating using this method. It's really a method or an algebraic technique to simplify the integral. So the idea here is to use this fancy algebra technique, simplify a complicated integral into a simple integral that hopefully we can be able to do using our table of integrals or some other method to simplify it further. This method is similar to u substitution, but we're going to be using trig functions when they don't apparently apply. So it's motivated by the trigonometric Pythagorean identities. If you remember back from your trig course, we have like sine squared plus cosine squared equals 1. If you just move that around a little bit, you get 1 minus sine squared is equal to cosine squared. So when we have something like 1 minus u squared, we're going to be using the substitution u is equal to sine to make this 1 minus sine squared, which converts to cosine squared. And likewise, if we have 1 plus u squared, we're going to be using the substitution u is equal to tangent, and that's motivated by another of those trigonometric identities. And the last of the possibilities would be u squared minus 1, and that would necessitate us using cosecant theta in order to take advantage of this trigonometric identity that cosecant squared theta minus 1 is equal to cotangent squared. So really what you need to know are these guys right here based on the type of like square that you have. 1 minus u squared, 1 plus u squared, or u squared minus 1. If you're going to have like a sum or a difference of squares, it's going to be one of those three types. Let me show you how that works with a simple example. All right, so for example A here, I have 1 over 1 plus x squared. And then we want to notice that there's a square there, sum of squares, 1 squared plus x squared, or just 1 plus a square. And we want to match up which of these guys does that look like. And that looks like this middle one, 1 plus u squared. Instead of u, it's x. But we want this thing to be our u, which means x. And the substitution is u is equal to tangent theta. So the thing being squared is x. So the thing being squared is equal to x tangent. The thing being squared is equal to tangent theta. So that means we have a substitution. Substitution. All right, I got to make that look a little bit nicer. Substitution is the thing being squared equal to tangent theta for this type of squaring situation. All right, hopefully I can get more on track without having to erase so much, but I'm trying to just use this this substitution u is equal to tangent theta, where the u, the thing being squared, is just x. So it's supposed to look much simpler than I just had to make it look with making a couple of mistakes. Sorry about that. So now we're going to go ahead and make the substitution. And since x is equal to tangent, we can put that in there. So this becomes the integral of 1 over 1 plus tangent squared, because it's x squared. So x squared is tangent squared. And if you're remembering the dx's, as I've talked to you about before, you'll notice there's still dx over here, which means we have different variables. We have a theta variable that we just introduced using our substitution, and we still have the x variable trapped inside the dx. So just like in our u substitution, we're going to have to solve for dx to put that in there. Well, in this case, x is the outside variable, and theta is the inside variable. So if I differentiate, I'm going to be differentiating with respect to the input variable, which is theta. So I do d theta on both sides. So this is your derivative of like dy dx, but there's no y. The output variable is x, and the input variable is theta. So we do d theta, which gives us dx d theta. And over here, we have the derivative of tangent theta, which is secant squared theta. And then, well, there's no chain because you get d theta, which is just 1. So we're not going to even bother writing that. So you just get secant squared to theta. Okay, so we're going to solve for dx. So knowing this, we could just move the d theta over on the other side, and we get secant squared theta d theta. And that's what we're going to put in for our dx. All right, so putting that or completing the substitution, we get 1 over 1 plus tangent squared theta times dx, which is secant squared theta d theta. Now, the reason for doing this substitution, reason for doing the x equals tangent theta substitution, is to take advantage of the Pythagorean identities. The middle one, 1 plus u squared, takes advantage of the fact that 1 plus tangent squared is equal to secant squared. And you'll notice we have exactly 1 plus tangent squared, so we know that can be written as secant squared. And lo and behold, we have a factor on the top, a factor on the bottom. They're identical, and we can divide those out or cancel them out if you wish, and you end up with just the integral of 1 d theta. And the question is, did it get simpler? And the answer is yes, it got as probably as simple as you could ever get. We're just anti-differentiating 1. The antiderivative of 1, I'm going to bring it down over here a little bit. The antiderivative of 1 is just the variable. Now it's d theta. So the antiderivative of 1 is not x, because that would be the antiderivative of 1 dx. The antiderivative of 1 d theta is theta. Theta is the variable in this integral. And oops, I don't need the integral sign anymore. I'll do equal sign. So we get theta, and then we get our plus c, of course, from integrating. Now, just like in the previous substitutions, you'll have to put your answer back in terms of the original variable. And looking at this problem, the original variable was x. So we need to get this back in terms of x. And just like in our previous substitutions, the way we get the variable back into x, or our original variable, is by using the substitution we made up. This is the substitution we made up. I'll write it over here. X equals tangent theta. And so we're going to use this original substitution just to substitute back into the original variable. Now we have to know what theta is, and our substitution isn't solved for theta. Our substitution says x equals tangent theta. So we're going to have to take this thing and we're going to have to solve for theta. So this requires a little bit of knowledge of trigonometry. To solve for theta, we have to get rid of tangent. Dividing by tangent doesn't get rid of tangent. You have to use the inverse tangent. So inverse tangent of x equals, I'm running out of space, sorry about that. More to the right. And over a little bit, please. Okay, so tangent inverse of x equals tangent inverse of the tangent of theta. So what I did was I took this equation and I took the inverse tangent of both sides. So I can always do the same thing to both sides. I do the inverse tangent of both sides. But nicely, the inverse tangent and the tangent are inverse functions. And so they undo each other. So we're left with just theta. So we get inverse tangent of theta, or inverse tangent of x, excuse me, is equal to just theta over there. So that we can put that back into our answer. And that would give us a final answer of tangent inverse x plus c. So there's a demonstration of using the trigonometric substitution, to simplify this integral to be able to find the answer and then substitute back and get the final result. Now, some of you who are good at recognizing things or with a good memory may realize that the integral of 1 over 1 plus x squared might be on your list of integration formulas. So you can go look at the common integral formulas and see if you have that. I think for me, it's number 25. So arctangent is the same thing as inverse tangent. So this is a formula. I wanted to show you how the technique worked, even though we could have actually just looked this up on our common integration sheet. There will be much more complicated ones that we won't be able to look up, but I wanted to show you just a basic one and how it worked at the start. Okay, so that is the idea of integration by trigonometric substitution. I'm going to try to keep those different substitutions handy. Let me clear off some of this ink so it's easier to see. And we're going to do each of these problems. I think I have 5 more problems or so. We're going to do each of these problems using this guide up here of what substitution to use for what type of squaring problem we have. right? And it's usually two things being added together or subtracted together. That's what we're going to do for this, squaring problem, this integration by trigonometric substitution. Okay, enough talking. Let's do another example. So for example B, I have 1 plus x squared again. So same formula. We have the 1 plus u squared, 1 plus a thing being squared, u just representing whatever you want being squared. In this case, it's just x being squared. So once again, I can use x is equal to tangent theta. And it's the same process, right? The thing is, this problem is different than the previous one because in the previous one, we had a 1 on top. On this one, we have an x on top, right? So it's going to be a little bit different when we do the substitution. So let me show you what we get here. If I take the derivative, I take the derivative with respect to theta. So I get dx d theta is equal to secant squared. We did this before, which means that dx is just secant squared d theta d theta. Okay, so now we're ready to do the substitution. So this guy here, I'll put it over here, is equal to the integral. So x is on the top. We know x is tangent theta. We have 1 plus x squared, so 1 plus tangent squared theta. And then we have dx, and dx we know is secant squared theta d theta. So that's our substitution. Now, this needs to have gotten simpler. Otherwise, we're not doing a process which is going to be helpful. So we want to make sure that the new thing we get is actually simpler than what we started with. And let's simplify this to see if indeed that's the case. Remember, the reason why we're doing this substitution, 1 plus x equals tangent theta, is that 1 plus tangent squared theta can be simplified as secant squared theta. So remember, we got this simplification here. 1 plus tangent squared is equal to secant squared, and that's why this substitution is a good one to try, because it takes advantage of that Pythagorean trigonometric identity. So we have the tangent on top. 1 plus tangent squared is secant squared. And now you can see how the secant squared on this on the bottom and the secant squared on the top are going to divide out, kind of like last time. So these guys go away. And I'm left with just tangent theta d theta equals integral of tangent theta d theta. So there's different ways of doing tangent theta. You can write this as sine theta over cosine theta, and then use a u substitution, or I guess we can't use, I don't think we've used, I'll use w just in case. So we can do w is equal to cosine theta, and that substitution works very nicely. So you can do like a w substitution and get that. But tangent theta is also on our list. So I'll just go to the list. Where's tangent theta? It's number 9 on my list. The antiderivative of tangent x dx is ln of secant x plus c. So I'm just going to do that. But if you didn't remember this or you didn't recognize it, you could still do it just using a normal substitution. So this integral is simpler than the original one. The original one was x over 1 plus x squared dx. And this one is just tangent theta, which is literally on our list. All right, so the integral of tangent is ln of secant theta plus our magical c. And we have to get it back in terms of the original variable x. Well, we could certainly solve for theta. We know what theta is. If we just take this thing and we take the inverse tangent of both sides, we get this kind of creature as we did before, right? It's the same thing we got before. But if I put that in there, we get the secant of the inverse tangent of x, and that needs to be simplified. So if we put in this version of theta, we get secant of the inverse tangent of x, and you have to be able to convert or simplify secant of inverse tangent, and that's challenging for most students. So I'm going to show you the standard trick or standard technique for how to get other trig functions. Like we know that x is equal to tangent theta. I mean, that's the substitution that we used. So how do I use this substitution to find sine theta or cosine theta or secant theta or anything else, right? So there's a standard way of doing it. And it's just to use our old like trigonometric definitions, like tangent is y over x or opposite over adjacent, right? If you remember your triangle thing, We got an angle here, a central angle theta, and then you have the y and the x, or many of you think of this as opposite and adjacent, right? And we know tangent is just the y over x. So this should be a fraction. So think of this as x over 1 if it helps you. So tangent is the y over x, or opposite over adjacent. So this side must be x, and this side must be 1. So opposite over adjacent is x over 1. And then we can use the Pythagorean theorem, 1 squared plus x squared equals c squared, this being my diagonal, my hypotenuse. And so we can know that c is just the square root of 1 plus x squared. Now, using this little triangle, I know the sine is x over the c. So it's, or the opposite over the c. So it's x over square root 1 plus x squared. Or cosine is the x over the c. So cosine is this 1 over the c. So you could just get all of your trigonometric things. So what is secant? Well, secant, if you remember what secant is, it's the upside down of cosine. So instead of the adjacent over the hypotenuse, it's the hypotenuse over the adjacent. So this is, I'll write it out using hypotenuse and adjacent, because I think a lot of students remember that from their geometry class. It'd be hypotenuse over adjacent. That's what I think a lot of people remember as the secant, right? Cosine is adjacent over hypotenuse. So secant is upside down, hypotenuse over adjacent. But given this little triangle that we drew out, or I drew out, I know what the adjacent and what the hypotenuse are. So the hypotenuse is our square root 1 plus x squared. And our adjacent is just, well, it's 1. So I mean, I guess we don't really need to write I'll write the 1 in there temporarily. But of course, we need to simplify this. So we would get rid of the 1 in our final answer. Just like that. And yes, there are more ways to simplify this, like 1 plus x squared square rooted is the 1/2 exponent, which can be brought in front of the log. So if you'd like to do that, that'd be great. You don't need to do it if you don't want to. This is things combined together. So that would be a great answer for this problem, ln of the square root of 1 plus x squared plus c. Okay, so that's an example of another trigonometric substitution where what we get at the end is some other trig function, and we have to solve back in terms of x. So being able to solve back in terms of x, perhaps doing the most popular method, like making a triangle, would be something you would practice in this section. One little side note, I did set up this problem for a couple of reasons. Just going back to the original problem itself, the original question was this integral. Some of you may have noticed that some of the people are just really good at spotting things. So some of you may have spotted right away that this problem can be done with just normal U substitution, or what I've been calling W substitution recently. Because if I make the bottom part the U, or in this case the W, just to try to keep things a little bit more straightforward, then I can solve for dW, and thus I can solve for dx. And it works out really, really nicely. This integral, I have x on the top, 1 plus x squared. Well, that's exactly what W is. And dx is W over 2x. The x's divide out. And I'm left with just 1, 2 comes outside. I'm left with just 1 over W dW, which is, well, the antiderivative of 1 over W is ln of W. And then I can put in the original variable x because it's already solved for W. And that is equivalent to our answer before. The reason why it looks different is because the 1/2 exponent can be put on top of the argument, and that's a square root. So the 1/2 exponent is the same as the square root. So this answer using W substitution is identical to the answer we did using trigonometric substitution. I don't want you to do problems two ways, but I do want to kind of show you that you don't always have to use a sledgehammer. Sometimes problems have multiple approaches, and you get to choose which one you want to use, unless the directions specifically say, like, use this technique. You can do whatever method might be easiest. I think for this section, I'm going to be showing you trigonometric substitution because I'd like you to practice that. But I did want to show you one as an example that can be done using a different technique, perhaps an easier technique than trigonometric substitution. All right, so my segue is a little bit over there. So let me go to another example so you guys can see some more complicated versions of trigonometric substitution. They do get more complicated just in terms of what they look like and how you have to simplify it algebraically. We're still using the exact same three versions of our trigonometric substitution that I showed before. Nothing is going to change about these guys up here. But the problems you'll see get a little bit more messy. So we have to deal with the mess as it gets more complicated. All right, so here we go. So more problems for us. Letter C, we have 1 over x squared, 1 minus x squared. And I don't have the formulas written down here, but if you refer back to the previous page, if you've printed out these notes, you'll notice that 1 minus something squared is going to be a sine theta. So 1 minus thing squared, we're going to have thing is equal to sine theta. So let me write that over here. Let me just make this more sizable over here. So we get 1 minus u squared. That means we're going to be using u is equal to sine theta. That's the standard substitution when we have 1 minus thing squared. All right, so I guess I should zoom in a little bit here because the screen's hard to see. It's hard to see for me, so I think some people may be viewing this on a phone or something, a small screen. It may be hard for you to see too, so hopefully that's better. I have the integral of x squared 1 minus x squared. So my 1 minus x squared, that's the 1 minus u squared thing. So the thing being squared is x. So I'm going to make x equal to sine theta. And then dx is cosine theta, d theta. And I can put that stuff in there. All right. So I'm going to substitute x is in and dx is in, just like in any kind of substitution problem, we do it the same way. So we get, oh, let me make that a smaller pen size. And let me make it green. All right, so we get equals 1 on the top, x squared is, well, x is sine theta, so we can do sine squared theta. And then we have 1 minus x squared in a square root, so we get 1 minus sine squared theta in a square root. And then we have dx. dx is cosine theta d theta. So I'll just put it up here, cosine theta d theta, so I don't use too much room. So I put my dx in there, put my x's in there, and I get this big old mess, which doesn't look promising, but let's simplify it first before we make a judgment on whether it got simpler. So the top we get cosine, the 1 we don't need to write. The bottom we have the sine squared thing. And the reason why we did this trigonometric substitution 1 minus u squared was to take advantage of the trigonometric identity. 1 minus sine squared is always equivalent to cosine squared. That's the old sine squared plus cosine squared equals 1 thing, just rearranged. So this is the square root of cosine squared. So the square root of cosine squared is going to be cosine, and we have a cosine on the top and a cosine on the bottom that are dividing out. And what do you end up with? You end up with, on the top, you just have d theta. On the bottom, you just have sine squared. And here's where remembering those trig identities are going to be helpful. 1 over sine is called cosecant. If you remember your trig formulas, I have a trig formula sheet on Canvas for you to look at. But it'll give you basic ideas of how to do these things. So cosecant is 1 over sine. It's this one on the top here, definition of 1 over sine is equal to the cosecant. So I'm going to do that one. And we have two sines on the bottom, so that gives us cosecant squared. And now if you go to your trig formula sheet, integral formula sheet, you will notice that cosecant squared is one of our known integrals. For me, on this sheet, it's number 14. The antiderivative of cosecant x squared is negative cotangent x plus c. So this is negative cotangent theta as our variable plus c. So did the integral get easier? It started with this guy up here. And obviously we know how to do this because it's on our sheet. So yes, it definitely got easier. That's the benchmark. That's the test on whether or not what you're doing is correct, is making sense. Is the new integral easier than the original integral? And the integral of cosecant squared is known. It's just negative cotangent. So yeah, so it's definitely easier to do. We could just look it up on our list and we get the answer. Now we're not quite done, of course, because we do not have our answer using the variable that we started with. Our answer has cotangent. That's a cotangent there, if it's not readable. And it has theta. And our original substitution, x equals sine theta, doesn't really tell us how to simplify that. Of course, you could write this as cotangent of inverse sine of x, but that's not going to be full credit. You got to be able to simplify it as well. And once again, my recommendation is just to make a triangle. So x equals sine theta. So we're going to make our little triangle with our central angle of theta. And we have the, the opposite, or the y, and the adjacent, and the hypotenuse, right? So we have the x and the y, and the hypotenuse, or the c. And we know that sine is x. Sine is opposite over hypotenuse. So if you'd like to make this into a fraction to help you see what to do, it's x over 1. So the opposite has to be x, and the hypotenuse has to be 1. And then you can use the Pythagorean theorem to find out that the adjacent here is equal to the square root of 1 squared minus x squared, or 1 minus x squared, which is coincidentally exactly what we started with here. Okay, so now that we have our triangle filled out with the adjacent equal to the square root thingy thing, the opposite equal to x, and the hypotenuse equal to 1, we got to figure out what cotangent is. So cotangent, if you remember or if you look on your trig sheet, right? What is cotangent? Cotangent is cosine over sine. Cosine is the adjacent, or the x. Sine is the y. So we just do cotangent is adjacent over opposite, which is the upside down of tangent. All right, so use this if you want to get a little bit of help with those formulas. So we know that cotangent, right? Cotangent. I ran out of room. I'll just erase this here. So what is cotangent? Cotangent of theta is the adjacent over the opposite, according to our formula. And that's equal to what? The adjacent is the square root thingy thing. And that's the adjacent thing, and the opposite is x. So that's the thing that goes in for cotangent. It's that crazy fraction right there. So that gives me my answer of negative cotangent of the square root of this thing over this thing. Let's see. All right, so there's another example of doing our trigonometric substitution. And this one, we had lots of stuff to simplify, and we used the trigonometric substitution x equals sine. All right, my next one is similar to the last one, but I kind of have a pair here. Before I had 1 over x squared, 1 minus x squared. And you'll see it's almost the same. I have 1 over x squared, 9 minus x squared. So I put a 9 in there. So if you are remembering, the idea of this thing is we're using the trigonometric identities, the Pythagorean identities. So like 1 squared minus sine squared is cosine squared. There's no 9 squared or 3 squared minus thing. It's always got to be a 1 there. So what do you do if there's a 9? Like, what do you do if there's a 9? Well, you're going to have to change it a little bit to make it come out to be 1. So I'll show you the way I look at it, and then I'll show you the way the book does it. So let me zoom in a little bit here. So we want this to be a 1. We really, really want that to be 1, right? So what we can do is we can just factor out a 9. We could just take the 9 away. If you factor out a 9, it becomes a 1. So what's that going to look like? So we have 1 x squared square root, and inside the square root, I'm not going to do 9 minus, I'm going to take a 9 out. If I take a 9 out of the 9, what's left over is 1, but there's no 9 in x squared. So a lot of students are like, well, how can I take a 9 out of x squared? Well, my friends, you just get a fraction. You just get x squared over 9. right? You're dividing it out, right? So if you could just think about, remultiplying it in, 9 times 1 is 9, 9 times x squared over 9 is just x squared. So we're just taking it out so that we get a 1 in there instead. Okay, and I'm going to write this again one more way, just to emphasize that we have to do 1 minus u squared gives the substitution u is equal to sine theta. So what's the thing being squared there? I know x is being squared, but what about the 9? So the way you need to think about this is the thing being squared here. The thing being squared there is both the x and the thing that creates 9, which is x over 3. So if you think about x over 3, x over 3 squared is exactly x squared 9. So that's the thing being squared. X over 3 is the thing being squared. So for our substitution, we're going to use the thing being squared is equal to sine theta. Oops. 3. Here's the thing being squared is equal to sine theta. Here's the thing being squared is equal to sine theta. Right? So that's you just factor out. So you have a 1 in there, and then whatever you need to have being squared, that's what has to equal sine theta. Now, our textbook, there we go, says that if the number isn't 1, if it's like a squared, so if you have a squared minus u squared, then that says you should use the formula u is equal to a sine theta. And that's the formula C. And when I learned calculus, that's the formula they taught me, a sine theta. But I'm like, why is there an a there? Why does it work? So I just wanted to show you the reason it works is we're just factoring that a squared out and square rooting it, and we get the a. And you can see that in my version over here. I just multiply both sides by 3, and I get 3 sine theta. So it's the same substitution. We have both times because our thing being squared in our 9 minus x squared thing is x, and our a is 3, and you get the exact same substitution. X equals 3 sine theta. Use whichever version you like. I like to show things the way that sort of you can make sense of them instead of just trying to memorize them, because eventually, if you don't use it a lot, memories will fade and you won't remember what trigonometric substitutions do or why they even work. So I thought I'd show you the factoring thing, and you can see why it has to be x over 3, because that's the thing being squared. I don't know if that helps anyone. There you go. All right, so let's do our substitution and finish off this problem. So of course I need to find, oh, my dx got fallen off. So I have to find what dx is over here. The derivative of 3 sine theta is 3 cosine theta d theta. And then all that stuff's going to go in there. And this problem's going to end up being almost identical to the previous one, because the only thing changed was the 9, and that's just going to change to 3, which we're going to take out. So I'll show you what that looks like. So I have my 1, my x is right here. So x squared would be 9 sine squared, because I have to square the 3 and the sine. And then I get the square root of 9 minus x over 3 squared. Well, x over 3 is sine. So we get sine squared theta. Where did I lose my, I lost my 9 on the outside. Okay, so I had to fix this. Anyone notice my mistake? So I made a mistake when I went from here to here. And although I hate making mistakes on video, I do want to emphasize that math people are not the people who just do everything flawlessly. We make several drafts, and then we come to a conclusion of how to do it. And within those drafts, we do make some mistakes. And so I like to honor that and show you that I do make mistakes like every other math person. So let me see if I can fix my mistake. So I didn't include stuff in here correctly. So let me do this again. Maybe some people noticed it and wondering what I was doing. So I apologize if you were getting confused. But I have a 9 on the outside. And I have parentheses 1 minus, this is x squared over 9, which is x over 3 squared. I think that undermined a little bit my explanation because I made a mistake when I was trying to explain it. But if you just factor out the 9, what's left in the inside is 1 minus u squared. And 1 minus u squared is the thing that we're going to be using our trigonometric substitution for, where the u is equal to sine theta. So this one's correct because my u is x over 3, and that's going to be sine theta. So we end up with 1 minus sine squared. All right, so I think I made my correction. So let me see if I can redo the substitution and it comes out correctly. So 1 on the top, x squared. Well, this is where x is. So x is 3 sine theta. So that would be 9 sine squared theta. So I think I had that from before. And then the square root part is where I messed up. So let me see if I can get that right this time. I have a 9 parentheses 1 minus x over 3 squared. X over 3 is just a sine theta. So x over 3 squared would be sine squared. And then I do have a dx on the top. So the dx is this 3 cosine theta d theta. So the dx is right here. So I can put that in for the dx. All right. So what do I now have? What mess do I end up with now? I get the integral. I have a 3 on the top and a 9 on the bottom. So I'll just take those outside. 3 over 9 or 1 over 3 if you want to make that simpler. I have a cosine theta d theta on the top. I have a sine squared on the bottom. And I have the square root of 9, and then 1 minus sine squared. Well, the whole purpose of this is to use the trigonometric identity. 1 minus sine squared is equal to cosine squared. And the square root of 9 is going to be 3. The square root of cosine squared is going to be cosine. And we're going to be able to simplify this even more so. So this is 3/9, which is 1/3. Cosine theta d theta. I don't know. I think I said one thing and I wrote a different thing. 1 minus sine squared. 1 minus sine squared. Oh, which is cosine squared. Okay, so I think I wrote it correctly, but I couldn't read my own handwriting. See, I'm getting nervous because I already made several mistakes. So now I'm like paranoid I'm going to make another mistake. All right, it happens. I'll get over it. I'll get over it. So I have 1/3 on the outside. I have cosine theta d theta on the top. On the bottom, I have a sine squared. And I also have the square root of 9 cosine squared, which is just 3. Square root of 9 is 3. Square root of cosine squared is cosine. Okay, error-free. There we go. The 3 I can take on the outside. I'm going to try to save some space for example E. So I'm going to go over here a little bit. So here, what do I get? I get, well, I can take the 3 out, and the 3 out becomes a 1 over 9 because I have 2 3's in the denominator, and they're multiplied. And then I have a cosine on the top, divides out a cosine on the bottom. And I have a sine squared on the bottom. And that looks familiar because we did that last time. We had a sine squared on the bottom. We're going to have the same kind of integral before, but it's just messier because we have a 9 there and we have to like figure out what to do with it and factor it or take the 3 out or whatever we need to do. But we end up with this kind of result. So we end up with an extra 1/9 on the outside, but we still end up with the antiderivative 1 over sine squared is cosecant squared. And the antiderivative of cosecant squared is cotangent. And then we have to use our triangle to go back. We had to be real careful about using the substitution that we have. So the substitution we have is this one over here. I'll do it in, I guess I'll do it in black. This one right here. X over 3 is equal to sine theta. So let me make a little triangle out of that over here. So I have x over 3 is equal to sine theta. That was our original substitution. So let me make a little triangle with a central angle theta. Sine is opposite over hypotenuse, or y over c. So we get x over 3. We didn't have to put it over 1 anymore because it's already over 3. We could do the a squared plus b squared equals c squared thing and determine this adjacent side here is 9 minus x squared. right? So that's this thing converted into a diagram using our basic trigonometric definitions. And then we look for cotangent. Cotangent is the upside down of tangent. Tangent's like the opposite, the x over the square root 9 minus x squared. It's like the opposite of our adjacent. So cotangent is going to be just the reverse of that, just like I did before. So it's going to be 1/9. Cotangent is going to be adjacent over opposite. So it's going to be square root, square root 9 minus x squared over x. The reason why I'm pausing is I'm thinking I made a mistake in my previous answer, which means I've made so many mistakes in this video. Maybe I should reshoot it, but I don't want to reshoot it. I want to show you that, real people make mistakes and it's okay. You just have to kind of be aware that those happen and you need to correct them. So I think that's the correct answer because the adjacent is this guy and the opposite is this guy. So cotangent is this guy over this guy multiplied by 1/9. So why do I say I think I made a mistake before is because I think on the previous one, let me zoom out a little bit. On my triangle, where's my triangle? Opposite over here. The previous one, there's my triangle up here. So my previous one, I had a triangle over here. And I said the cotangent, we got cotangent of theta plus c, and cotangent, once again, is adjacent over opposite. And so the answer should be the adjacent 1 minus x squared over the opposite x. What the heck is this cotangent doing there? The cotangent is this thing. I wrote it right here. I wrote down my formula, and I didn't follow my formula. So let me put a red line through this because that's a mistake. Cotangent theta, according to my own handwriting, that's my handwriting there. Cotangent theta is square root of 1 minus x squared over x. So the answer to C, if I go back and correct it now, I'll write it over here. I need more space. The answer over here is negative of cotangent, and cotangent is this critter right here. Yeah. I wish I didn't make those little mistakes because sometimes people see it and they get the wrong idea and they don't watch the rest of the video. And then they forget to check that I corrected my answer. So this is the correct answer, not cotangent of that thing. Cotangent of theta is that thing, 1 minus x, square root of 1 minus x squared over x plus c. Okay, well, I did correct it. I did my little speech about, making mistakes and trying to correct them. And it's going to happen to all of us. All right. And it's important to find your mistakes. I didn't find my mistake, so maybe that's a good thing that I found my mistake. All right, so ultimately, I showed you an example D in which we didn't just have 1 minus x squared, we had 9 minus x squared, and how to deal with that. So let me give you another similar example to that, maybe a little bit more complicated, and that's example E. And I'm going to go a little bit slower and hopefully not make any mistakes. Again, that's just a hope, not a guarantee on this one. So we have, again, a 1 minus x squared type deal, but we have 16 minus 25x squared. So this is, do a blue or something. This is 1 minus u squared-ish. I know it's not because there's like a 16 and a 25 and stuff. So, but it's like 1 minus x squared. It's just got a bunch of numbers in there. So we're still going to use the idea of sign. We still have to get rid of the 16. So I'm going to factor out the 16, just like before. X square root. There's a 16 that I need to factor out, so it becomes a 1. The goal here is to make a 1. And then I factor 16 out of the 16, there's 1. I factor 16 out of the 25. Well, it doesn't really work well, but I just make a fraction just like before. This kind of factoring, once you get used to it, is very, very handy. There's a lot of problems in Calculus 2 and Calculus 3 where this kind of factoring where it's like, well, I can't really factor because it's not there. You can factor anything you want. You just have to make it into a fraction. It comes in really handy. Surprisingly many problems where this kind of factoring from nowhere is really helpful. So if you kind of see it now, it kind of like makes things easier in the future as well. All right. So what is my thing being squared? My thing being squared. So I get 1 dx on the top. On the bottom, I have x. square root, I have the 16 there. 1 minus, I need this as a square, right? It's got to be u squared. So what's being squared? Well, the x is being squared, 5 is being squared, and on the bottom, 4 is being squared. So I'm going to write that as 5x over 4. That's supposed to be a 5. It's hard to see. 5x over 4 being squared. That's the thing being squared on the bottom. So that's my u right there. That's my thing being squared. U squared is 5x over 4 being squared. So we have 1 minus u squared as long as we let u be this thing right over here, right? 5x over 4, right? But our substitution is u is equal to sine theta. So we just put these two together and get 5x over 4 is equal to sine theta. I find one of the hardest things about doing trigonometric substitution is just trying to find the exact right substitution to do. Is it sine? Is it tangent? Is it secant? Where are all the numbers going to work out? You know, that kind of stuff turns out to be like very detail oriented. And as you noticed, I haven't gone slow enough to avoid little mistakes. So, you know, just be a warning. You can also write this as 5x equals 4 sine theta, which is more like a textbook would write, or you could write this as x equals 4/5 sine theta, which is kind of solving for x. It doesn't really matter. All these are equivalent, but you do need to find dx at some point because you're going to have to put that into the formula. The derivative sign is just cosine. And we get a d theta because this is dx d theta, so we get a d theta over there. Okay, so let's go ahead and make the substitution. Let's verify that it got easier and then hopefully find the answer to this problem. All right, on the top, we have 1 dx. 1 times 4/5 is just 4/5 cosine theta d theta. On the bottom, I have an x, which according to my little chart here, x is 4/5 sine theta. And then I have a square root. That square root is, well, the square root of 16 is going to be 4, but I'll leave it as a 16 right now. And then I have inside 1 minus 5x over 4 squared. We know what 5x over 4 is. 5x over 4 is sine. That was our original idea to make that thing being squared. So 5x over 4 squared is literally just sine squared. And yes, indeed, we get our 1 minus sine squared simplifying to cosine squared because of that identity that we like using. Looks like I forgot my integral sign. So let's throw it in there. It does look like I have a 4/5 on top and a 4/5 on bottom. So that's nice that those divide out. So what am I left with? I'm still left with the integral. I haven't done any integration yet. I have cosine theta d theta on the top. And what do I have on the bottom? I have a sine theta. Let me square it, that 16 right now. It's a 4. And then I have 1 minus sine squared, which is cosine squared. And the square root of cosine squared is cosine. So you might see that I have a cosine on the top, and I have the square root of cosine, which is a cosine on the bottom, and those will divide out. I can take my 4 to the outside and write that as a 1 over 4. And then I have this thing right here. Integral of just d theta on the top and just sine theta on the bottom. All right, is it simpler? Well, it definitely looks simpler to me than the original integral. The integral here was x squared 16 minus 25x squared, and I just have sine theta. Even if trig is not your favorite thing, you might recognize this is just a sine theta or 1 over sine theta, much simpler than this crazy x squareds and stuff that we had originally. All right, so we're going to write this in terms of not a fraction, so we can do our trig formulas. 1 over sine is just cosecant. And the antiderivative of cosecant is one of our standard formulas. On my sheet, it's, where is it? Number 12. The antiderivative of cosecant x dx is natural log cosecant minus cotangent. So this is natural log of cosecant minus cotangent. And I'm running out of space. Cosecant minus cotangent. And then, of course, we get our plus c. All right, last bit of these very long problems is put everything back in terms of the variable that we like, or that we started with at least, which is going to be our x's. And to do that, we go to our original substitution, which is this guy up here. Sine x is equal to 5x over 4. I make my little triangle with central angle theta. Sine is opposite over hypotenuse, so it's 5x over 4. And then I can use my Pythagorean, or my a squared plus b squared equals c squared, to find this is 16 minus 25x squared. C squared minus a squared is b squared. And you might notice that that's exactly kind of what the integral started with. That's not just a coincidence. You're going to see that over and over again. See there, 16 minus 25x squared. 16 minus 25, it comes up again, right? So in the triangle. All right, so what do we need? We have our answer being 1/4 ln of cosecant. So cosecant is the opposite of sine. So sine is 5x over 4. So this has got to be the reverse of that. It's got to be 4 over sine x. Right? So that's got to be cosecant. It's just the flip of sine. And then cotangent is the flip of cotangent. So cotangent, or tangent, is opposite over adjacent. So we have to do the reverse of that. To do cotangent, we have to do adjacent over opposite. So it's going to be minus, and then adjacent is this square root 16 minus 25x squared. And then the opposite is 5x. And then we move this over a little bit and put our plus c, and then we got our answer. This can't be sine x here. What did I do wrong here? Oh, it's 4 over 5x. I think I said 5x, and I wrote sine x. My apologies. I was trying to do it error-free. I think I made it right to the end. I got excited and celebrated too early. Just to repeat, cosecant is the opposite of sine. Sine is like opposite over adjacent. So we have to do the reverse. We have to do the reverse of opposite over adjacent. So that would, opposite over hypotenuse. So the opposite, the reverse of opposite over hypotenuse, the cosecant is hypotenuse over opposite. All right, so it's 4 over 5x. And for some reason, I wrote a sine there. I confused myself. Okay, well, mostly error-free, right? Mostly error-free. So that's the answer right there, using trigonometric substitution. Will I be able to do any of these problems flawlessly on this video? I hope I do at least one flawlessly in this video. But that was one in which we had more numbers to deal with, and we had more things to substitute at the end. So my goal for this problem was just amp it up, more difficulty, more numbers to worry about when you're factoring to get the right substitution. And then when you're substituting back in, more things to try to worry about substituting back in. So that is stepping up a little bit. I'm going to do 2 more problems in this video. I'm not sure if they're much more difficult than this. There are a little bit twists to those things. I'll show you what those 2 are, and then that will finish my demonstration problems on the integration by trigonometric substitution. All right, so these are the last 2 problems I was talking about. So the antiderivative of 1 over 1 minus x squared dx. And the reason why I have this one is that for those of you who are reading the textbook, which is great if that's helpful for your learning process, there's a statement in the book about the necessity for having square roots. The way they put it is, if you have something like the square root of 1 minus u squared, then you're going to make u is equal to sine theta. And what I say is that if you have 1 minus u squared, then you use u is equal to sine theta. So that was what I put on the beginning of these lecture notes for 7.3. I don't have the square root there. And the reason why is because it's not necessary. Example F is a simple problem where I have 1 minus u squared, 1 minus thing being squared, 1 minus x squared, and there ain't a square root to be found. And yet this is a perfect example of a problem that can be done using trigonometric substitution. So I think the author wasn't really clear that you don't need a square root. It's common. It's common to have a square root, but it's not needed to have a square root. So I have a couple of problems here, F and G, where there are no square roots. And yet it's still trigonometric substitution. So kind of keep that in mind if you're taking notes from the book. It's a little bit misleading about having square roots in these types of problems. All right, so let's just do this problem. I stripped away all the weird numbers and stuff just to make it straightforward and talk a little bit about the necessity for square roots and to do this problem once again, showing that it can be done and showing another example of trigonometric substitution. So this is a 1 minus u squared type deal. So we're going to use sine theta. So a thing being squared is x. So thing is equal to sine theta. And then dx is equal to cosine theta d theta. And now let's do our substitution. So we get 1 over 1 minus sine squared because x is just sine. And then dx we know is cosine theta d theta. And then 1 minus sine squared is cosine squared, because the whole reason why we're doing this is to use that identity. And we have a cosine on top, d theta. So there's a cosine on the top and a cosine squared on the bottom. So one of the cosines on the top divides out one of the cosines on the bottom, if that is clear what I'm doing there. And so I have 1 d theta on the top, and I have just 1 cosine left on the bottom. And let's get rid of the fraction so we can do some anti-differentiation. 1 over cosine is called secant. And integral secant, again, one of the formulas on our sheet. Integral secant is number 11. It's natural log secant plus tangent. So this is natural log secant plus tangent. Plus c. And then let's take our original substitution. Original substitution was over here, was x equals sine theta. So put that over here, x equals sine theta. Draw our little triangle with a central angle theta. Sine is opposite over hypotenuse, or the y over the r. And so we need to think of this as a fraction. You can write this over 1. So we get x over 1, and then do the a squared plus b squared equals c squared, and discover this is 1 minus x squared. And they'd be shocked and amused that this is the same kind of thing we started with, 1 minus x squared. I mean, it's not a square root, but again, square roots don't really matter in terms of when to use this stuff. You still have the 1 minus x squared, which is the kind of thing we started with. Okay, so secant, let's try to get this right this time. Secant, well, cosine is the adjacent over the radius, or adjacent over hypotenuse. And so we need to do this backwards. Cosecant is just the upside down of cosine. So we'll do hypotenuse over adjacent. So I get my ln. Secant is hypotenuse over adjacent. So 1 over the square root of 1 minus x squared, plus tangent. Tangent is just opposite over adjacent, so opposite over adjacent. So that's x over the square root of 1 minus x squared, and the ln, and plus c. And I think I did it, my friends. I think I got it right without having to erase. I think that is the correct answer. Pretty sure of it, actually. So that's the antiderivative of 1 over 1 minus x squared. No square roots necessary in the original problem in order to do it. We did the trigonometric substitution. We ended up with this new integral, which was much easier to do than the old integral. The old integral of 1 over 1 minus x squared. It doesn't really work with integration by parts too well. It definitely doesn't work with W substitution. It's a very nice problem to do with trigonometric substitution, as you can see, it comes out pretty straightforward. I mean, once you learn this process and don't make little mistakes that you have to fix, it comes out very straightforward. All right, one last problem for you with another little twist to it. So that's letter G, and then I promise I will only do more upon request instead of in this video. So I know it's going to be a long video as it is. All right, so this G guy here, it has x squared in it, and it has a 13, which is kind of a weird number, but also has 6x in the middle, right? This is definitely not like a 1 plus x squared or 1 minus x squared type deal. It has an x squared in it. It has some numbers, which we know we can factor out, but it's definitely not just a number plus or minus x squared. So what do we do with this thing? And the answer is we factor it, right? So we're going to factor this to make it look like sort of a 1 minus x squared kind of thing, or maybe x squared minus 1 sort of thing. So the type of factoring, you have to go back to your pre-calculus class, is called completing the square. We need to make this into a square. So if that sounds like familiar, that's what we're going to be doing. If you find it scary, that's okay. It's going to be not so it's complicated. So we want something being squared, and these things have to be the thing being squared. So we want something squared to be x squared minus 6x, and that's going to be x minus 3. And some people are saying, how do you know it's x minus 3? Well, I've been doing math for so many years. I know it's x minus 3, but now here's my reasoning. X minus 3 squared, if you know how to square stuff out, is x squared minus 6x plus 9, right? To get an x squared, you need the x. To get the 6, you have to do half of it, 3, because you're going to do a 3x and a 3x to get 6x. That's how you FOIL things out. You're always going to get that middle term twice. So you basically need the x, and you cut that middle thing in half. So half of 6 is 3, and it's got to be x minus 3. Now, x squared minus 6x plus 9, which is what this thing right here is your x squared plus 6x plus 9, right? That's not what we have up here, right? We have x squared minus 6x plus 13. So these have to be equal. And that's why I have an equal sign here. So they have to be the equivalent. They have to be the same thing. So some people, they have a plus 9 here. They write a minus 9 and a plus 13. This is what some people learn how to do in pre-calculus. Like if you put an extra plus 9, you put a minus 9 to balance it. You don't have to do it that way if you don't want to. There are many ways of doing it. One simple way is just saying, well, I know what x minus 3 squared is. I mean, we know what x minus 3 squared is, this thing right here. If I do it, I get a plus 9, but I'm supposed to get a plus 13. So I have to add 4 on here because 9 plus 4 is 13. So however you want to complete the square, you can complete the square. I know some people actually make an equation out of it. They make y is equal to x squared minus 6x plus 13. They subtract 13 on both sides. And then they complete the square just with the x's, right? So they just do this thing as x minus 3 squared. And then we get a plus 9 minus 9 like this. And then they put everything back together, right? So then they add 13 to both sides and they get something like this. So there are many ways of doing completing the square. I'm not sure what your favorite one of doing it is, but nonetheless, you always end up with the same x minus 3 squared plus 4. All right, this guy, by the way, is still x minus 3 squared plus 4. The one I have here in red for color-sighted folks. Minus 9 plus 13 is 4. So let me write this with the 4 in front, just so it looks a little bit more familiar. I have x minus 3 squared plus 4. Let me just write 4 plus x minus 3 squared. So it kind of matches up a little bit more with our trig substitution. So remember that 1 plus u squared, for that type, we use tangent because we have 1 squared plus tangent squared is secant squared. So we do u is equal to tangent in the plussing kind of things. Then you're saying, well, we don't really have 1 plus u squared. We have 4 and we have thing squared. It's got to be close enough, right? We're gonna muck with this a little bit to get 1 plus u squared. Don't worry. But visually, that's the closest one, right? It's definitely a plus, not a minus. And so we're going to be using sort of the idea of 1 plus u squared. So once again, we don't need a 4 there, we need a 1. So how do I do that? Well, I just factor 4 out. So on the bottom, I have 4 parentheses 1 plus, and there ain't no 4 in x minus 3 squared. So you may now know how to do this. You just make a fraction out of it. So there's a 4 down there. So then when you multiply back, the 4's cancel out and you're good to go. And you get 1 dx. Maybe I'll just write dx up there. I'm tired of writing the 1. Maybe I should erase and not highlight. There we go. So there's that thing. And so I need thing being squared. Now, x minus 3 squared over 4. The 4 is not part of the squaring thing, but let me just write that as a square. So we get dx, we get 4, we get 1 plus, 4 is really 2 squared. So let me just write this as x minus 3 over 2. That's the thing that if I square it, I get x minus 3 squared over 4. So I have 1 plus u squared, where this creature right here is my u. So u is equal to tangent theta, where u is thing being squared. My thing being squared is x minus 3 over 2. That's my thing being squared. So that thing is equal to tangent. And like I said before, in my opinion, that's kind of the hardest part of this process, is just figuring out the exact substitution to use, the right trig thing, where all the numbers go. In this case, we had the added complexity of having to factor it first so we can actually see what was being squared. So all that stuff, like setting up the substitution, I find the most challenging parts of these problems. Your opinion may vary, but for me, at least, that's the part where if I can do that right, I'm pretty confident I can do the rest. So let me multiply both sides by 2 just to simplify this a little bit. And I'll add 3 just to have it by x itself. If I had to square x, then I'd have to square 2 tangent theta plus 3, because that's what x is equal to. Let me go ahead and do my substitution. All right, so I think I'll switch colors at this point because this is where I'm doing my substitution. I have a dx on the top. The dx is, I didn't find my dx yet. Let me find my dx. Dx is, I'm doing the derivative of this with respect to theta. The 2 doesn't change. The derivative of tangent is secant squared. And the derivative of plus 3 is just 0, so I don't have to write that. Okay, so I have a dx on the top, so that's 2 secant squared theta. On the bottom, I have a 4. I guess I could take the 4 on the outside, right? I don't really need the 4. And then I have 1 plus this weird x minus 3 over 2 being squared. This is the x minus 3 over 2 squared. Since x minus 3 over 2 is tangent, then x minus 3 over 2 squared would just be tangent squared. And the idea here is we can use one of our Pythagorean trigonometric identities. 1 plus tangent squared, that's one of our trigonometric identities. You can look it up. I can remind you here, 1 plus tangent squared is written as secant squared. It's one of our standard trig formulas from your good old pre-calculus days. And so I can rewrite this thing. Oh, I was going to use blue and then I ended up using all green. So there we go. I'll switch to blue. 2 secant squared theta on the top. 1 plus tangent squared is secant squared on the bottom. And lo and behold, we have a lot of division here. Secant squared on the top, secant squared on the bottom. The 2 I can bring out. I did forget my d theta. dx d theta is 2 secant squared theta, which means dx is equal to 2 secant squared theta d theta. So I forgot my dx d theta thing, and therefore I forgot my d theta. So let me put that back there. Okay, so found a little mistake, corrected it as usual. So the 2 secant squared theta d theta on the top, and the 1 plus tangent squared, which is secant squared on the bottom, has the secant squareds like divide out, cancel out, and I'm left with a 2 on the top, so 2 over 4. Integral of everything is divided out. The 2 I took out, I'm left with just d theta. So what's the antiderivative of d theta? Well, 2 over 4 is 1/2. The antiderivative of d theta, or 1 d theta, or just, that thing, is the variable. It's not x because we're antidifferentiating d theta. The antiderivative is just theta. And then we get a plus c. And now we have to put theta back in terms of the original variable. And drawing a triangle is not going to help. Triangle, when I draw the triangle thing, for the theta, like tangent theta is x minus 3 over 2. There's my theta. Tangent is opposite over adjacent. There's nothing wrong with drawing the triangle for this problem, but The reason why we do this triangle is so we can find sine and cosine and cotangent and all those weird things, right? That's the triangle helps guide us into all the other trig stuff. We don't have sine, we don't have cosine, we don't have cotangent, we just have theta. So we don't really need the triangle for this problem. We just need to solve for theta. And I'll remind you, I did that on the very first problem. Let me just remind you real quick how to do it again. So we know our substitution is x minus 3 over 2 is equal to tangent theta. So we need to get rid of the tangent. We're just going to take the inverse tangent on both sides, or the arctangent if you're old school like me. And the inverse tangent and the tangent are inverse functions. They will undo each other and leaving just theta. This is a theta right here. So you're left with just theta is equal to this arctangent, inverse tangent of x minus 3 over 2. And that's what we put in for the theta thing there. All right, so we get 1/2 theta, which is this inverse tangent of x minus 3 over 2, and then our lovely plus c, and that is the antiderivative of this last example here, where we started with this very unappealing fraction, 1 over x squared minus 6x plus 13 dx, and we just factored it, and we used the substitution, trig substitution, and we got it to the end, and that's how you do trigonometric substitution. Lots of different examples of how it works. Please give these a try and reach out if you have any questions or want to try any other practice problems. I'd be very happy to help. All right, well, have a good day or good evening, and I hope I see you soon.